December 16th, 1944. Antwerp, Belgium. 5:57 in the morning. The sky was still dark, the city silent except for the distant rumble of Allied trucks moving supplies through the frozen streets. Then the sirens began. Corporal James Mitchell, a 21-year-old radar operator from Ohio, had been staring at his scope for 3 hours straight. His eyes burned, his back ached. The cramped trailer housing the SCR 584 radar unit smelled like cigarette smoke, burnt coffee, and the particular electrical ozone scent that all vacuum tubes gave off when they ran hot. He had been tracking individual German aircraft all night, vectoring anti-aircraft batteries onto targets, one plane at a time. That is how radar worked. One target, one gun solution, one engagement. Then his screen exploded with light. Not one contact, not two. 63 distinct radar returns, all moving at 240 miles per hour, all heading directly toward Antwerp harbour. 63 v. 1 flying bombs launched simultaneously from sites across occupied Holland. The Germans called it Vergeltungswaffe, the vengeance weapon. The Allies called it the buzz bomb because of the distinctive pulse jet engine sound that cut off seconds before impact. Each V1 carried an 1,800-pound warhead. 63 of them meant over 50 tons of high explosive about to rain down on the most important port in Europe. Mitchell did something that should have been impossible. He tracked all of them, not sequentially, simultaneously. His SCR 584 painted every single V1 on his scope, updated their positions every 3 seconds, calculated trajectories, and fed firing solutions to 16 separate anti-aircraft batteries within a 2-mile radius. For the next 11 minutes, the sky over Antwerp became a precisely orchestrated killing ground. American 90mm guns, British Bofors 40mm cannons, and M51 quad-mount 50-caliber machine guns all fired, in coordinated patterns, each weapon guided by data from Mitchell's radar. 57 vones second were destroyed before reaching the city. 6 got through. Those 6 killed 42 people and wounded 116 more. Terrible numbers. But without the SCR 584, all 63 would have impacted. The projected casualties were over 2,000 dead, 5,000 wounded, and the destruction of Antwerp's port facilities, which were supplying every Allied army in Western Europe. Mitchell saved the port. He saved 2,000 lives. And he did it with technology that, 3 years earlier, every radar expert in America had declared fundamentally impossible. Not difficult. Not impractical. Impossible. The kind of impossible that meant the laws of physics themselves forbade it. If you're enjoying this deep dive into the story, hit the subscribe button and let us know in the comments from where in the world you are watching from today. This is the story of how one man's theoretical curiosity, dismissed as useless by the military establishment, created the most sophisticated radar system of World War II. A system that could track 100 aircraft simultaneously, guide multiple weapons at once, and predict where a target would be 3 seconds in the future, with accuracy measured in feet, not miles. The Germans never understood how American gunners were hitting targets they could not see through clouds, at night, in conditions where visual aiming was worthless. They suspected radar. They built their own radar systems. But they never achieved what the Americans achieved. Because the SCR 584 was not just better radar, it was a completely different approach to the problem, built on physics that seemed too abstract, too theoretical, too divorced from practical engineering to matter in warfare. By early 1942, everyone understood that radar was critical to winning the war. The British had used it to win the Battle of Britain. The Americans were using it to hunt submarines and guide bombers. The Germans had their own radar systems, protecting their cities and guiding their night fighters. But every radar system in the world in 1942 had the same fundamental limitation. It could only track one target at a time. The operator would see multiple contacts on the scope, but to actually track something, to calculate its speed, heading, altitude, and generate a fire control solution, you had to focus on one target. Lock onto it, follow it, Ignore everything else until you were done. For anti-aircraft defense, this was catastrophic. German bombers did not attack one at a time. They came in formations, 20, 30, 50 aircraft at once. Your radar could see all of them as dots on a screen, but you could only track one. By the time you finished calculating a fire solution for the first bomber, the formation had already dropped its payload and turned for home. The math was brutal and simple. If it took 2 minutes to track a target and generate firing data, and the enemy sent 30 bombers, you needed 60 minutes to engage them all. But the bombers would be over the target in 8 minutes and gone in 15. The United States Army knew it needed better anti-aircraft radar. In 1941, they issued contracts to every major defense contractor: General Electric, Westinghouse, RCA, Bell Labs. The specifications were clear. Build a radar system that can track multiple targets simultaneously, calculate firing solutions automatically, and guide anti-aircraft guns with enough precision to hit targets through clouds. Every single contractor came back with the same answer: impossible with current technology. The problem was not detecting targets. Radar could do that. The problem was processing information. To track a target, you needed to measure its position multiple times, calculate velocity vector, predict future position, account for parallax error, adjust for atmospheric refraction, compensate for gun ballistics, and update continuously as both the target and the gun platform moved. For one target, this required mechanical computers, analog calculators, and trained operators working together. The computational load was enormous. Tracking 30 targets simultaneously meant 30 times the computational power. In 1941, that meant rooms full of mechanical calculators, hundreds of operators, and processing delays measured in minutes, not seconds. By the time you calculated where the target was going to be, it had already been there and left. RCA's chief engineer wrote to the War Department, "The processing requirements for true multi-target tracking exceed the capabilities of any computing system that exists or could exist within the next decade. This is not a radar problem. It is a fundamental computational impossibility." Bell Labs was more blunt. Their assessment stated, "What you are requesting violates the known limits of analog computation. Even if we could build a radar with sufficient resolution and update rate, the processing would require a computer weighing several tons, consuming enough power to run a small factory, and operated by a crew of 20 specialists. Such a system could not fit on a mobile platform and could not operate in combat conditions." The Army did not give up. They created the Radiation Laboratory at MIT, the same facility working on submarine detection radar and bomber navigation systems. They brought in the best radar engineers in America, and they gave them an impossible mission: build mobile anti-aircraft radar that can track dozens of targets simultaneously, fit on a truck, operate with a crew of 4, and be ready for field deployment by 1943. The engineers looked at the specifications and told the Army it could not be done. Then a 34-year-old physicist named Ivan Getting showed up with a solution so elegant, so counterintuitive, that when he first proposed it, 3 senior Elevi's engineers told him he fundamentally misunderstood how radar worked. Getting did not come from a military background. He had studied cosmic rays at Oxford as a Rhodes Scholar. Cosmic rays, the high-energy particles that strike Earth from space, useless knowledge for winning wars, abstract physics with no practical application. Or so everyone thought. Getting had been studying a problem that seemed completely unrelated to radar. When cosmic rays strike the atmosphere, they create cascades of secondary particles. To detect these cascades, physicists needed instruments that could measure multiple particle tracks simultaneously. Getting had developed a technique using rapidly switched detection systems that could sample multiple inputs faster than any single detector could physically move. The key insight was this: you did not need to track each particle continuously. You just needed to sample each position fast enough that your brain interpreted the samples as continuous tracking. It was the same principle behind motion pictures. Show someone 24 still images per second, and their brain perceives fluid motion. Getting realized the same principle could work for radar. You did not need to track each target continuously. You just needed to sample each target fast enough that the tracking appeared continuous. The math was beautiful. If you could switch between targets faster than the target moved significantly, you could create the illusion of simultaneous tracking with a single radar beam. Senior engineers told him it would not work. Harold Zahl from the Signal Corps laboratories explained patiently. Ivan, radar beams cannot switch instantaneously. The antenna has mass. It has to physically rotate. Even if you could move the antenna fast enough, which you cannot, the transmitter needs time to stabilize after each repositioning. Your pulse repetition rate limits your switching speed. This is not a computing problem. It is a hardware limitation that cannot be overcome. Getting's response was simple. Then we do not rotate the antenna mechanically. We rotate the beam electronically. That statement caused actual laughter. Electronic beam steering required phased array antennas, technology that existed only in theoretical papers. To steer a radar beam electronically, you needed dozens of transmitter elements, each precisely phase-shifted to constructively interfere in the desired direction. The precision required was absurd. Phase errors of more than a few degrees would destroy the beam pattern. Temperature fluctuations would throw off calibration. Component variations would make consistent performance impossible. Getting had not worked out all the engineering details. He just knew the physics said it was possible. He calculated that if you could switch the radar beam between targets every tenth of a second, sampling each target 3 times per second, you could track 30 targets, and the human operator would perceive all 30 as continuously tracked. The update rate would be fast enough to calculate velocity, predict position, and generate fire control data. Better than that, you could automate the entire process. Let the radar identify targets, assign tracking priority, calculate firing solutions, and output data directly to the gun directors. Remove the human processing bottleneck entirely. The radiation laboratory director was skeptical but desperate. Anti-aircraft defenses were failing. American bombers over Germany were being slaughtered by Luftwaffe fighters and flak. British cities were still under attack from German bombers. The Pacific theater was worse. Japanese air attacks were sinking ships faster than they could be replaced. If Getting's approach had even a 10% chance of working, it was worth trying. They gave him a team. 5 engineers, 2 machinists, a lab space in Building 20, and 6 months to prove the concept. Getting's first challenge was the antenna. Mechanical rotation was too slow. Phased arrays were too complex. He needed something in between. His solution came from an unexpected source: microwave relay towers. Before the war, Bell Labs had been developing microwave communication systems for long-distance telephone networks. These systems used parabolic reflectors that could be tilted slightly to aim the beam without moving the entire antenna structure. Getting adapted this concept. Instead of rotating a massive dish antenna, he designed a system with a fixed parabolic reflector and a small feed horn that could be rapidly repositioned. Moving just the feed horn, which weighed a few pounds, was far faster than rotating a 1,000-pound antenna assembly. The feed horn could sweep through 90 degrees in less than 1/10 of a second, fast enough to sample 30 targets 3 times per second with enough dwell time to get solid returns. But there was a new problem. Every time the feed horn moved, the radar's transmitter frequency would shift, slightly due to mechanical stress on the waveguide connections. This caused the receiver to lose lock, requiring recalibration after each movement. It took 2 seconds to recalibrate. That destroyed the entire concept. Getting's team spent 3 months trying to mechanically stabilize the waveguide. Tighter tolerances, better materials, vibration dampening, nothing worked consistently. Then, Mary Anderson, one of the electrical engineers on the team, suggested something that seemed insane. Stop trying to prevent the frequency shift. Compensate for it electronically. She proposed using a feedback circuit that would measure the frequency error and automatically adjust the receiver's local oscillator to match. Real-time frequency tracking. The senior engineers said it would not work. The feedback loop would be too slow, would introduce oscillations, would destabilize the entire receiver. Anderson built a prototype anyway, using 3 vacuum tubes and a handful of capacitors. Not perfectly. The tracking was noisy, and the loop would occasionally lose lock, but it worked well enough to prove the concept. Within 2 weeks, the team had refined the circuit. Frequency tracking error dropped to less than 1 part in 10,000. The receiver could now follow the transmitter regardless of mechanical drift. With that problem solved, getting turned to computation. Tracking 30 targets meant calculating 30 velocity vectors, 30 predicted positions, 30 firing solutions, continuously, updated 3 times per second. The mechanical computers available in 1942 could not do this. They were too slow, too bulky, too power-hungry. Getting needed something faster. The answer came from the same cavity magnetron technology that was revolutionizing naval radar. High-power microwave transmitters generated enormous amounts of waste heat. This heat was typically dumped through cooling fins and ignored, but Getting realized that heat was wasted energy that could be used to power thermionic computing circuits. By using the radar's own waste heat to warm vacuum tube computers, he could significantly reduce the external power requirements. More importantly, vacuum tubes could compute faster than mechanical systems. A mechanical computer needed physical gears to turn, rods to slide, cams to rotate. Each calculation took time measured in tenths of a second. A vacuum tube circuit could perform the same calculation in microseconds. The limitation was complexity. Mechanical computers could store state in physical positions of gears and cams. Vacuum tube circuits needed capacitors to store state, and capacitors leaked charge. Any calculation taking more than a few milliseconds would lose accuracy as the stored values decayed. Getting's insight was to not store anything. Instead of calculating a complete fire control solution and then storing it, calculate it fresh every time the radar updates. 3 times per second, the radar samples each target, feeds position data to the vacuum tube computer. The computer calculates velocity and predicted position, outputs the firing solution directly to the gun directors, then forgets everything and starts over. No storage, no memory, no state. Just continuous calculation, 3 times per second, for every target. This sounds wasteful. Why recalculate everything from scratch 3 times per second when you could calculate once and store the result? Because recalculating eliminated accumulation of errors. Stored values drifted. Fresh calculations did not, and vacuum tubes were fast enough that recalculating 30 targets 3 times per second was actually easier than building reliable storage for 90 values updated continuously. By September 1942, Getting's team had built a working prototype. It was ugly. Vacuum tubes, transformers, and capacitors spilled across 4 laboratory benches. Power cables snaked everywhere. Cooling fans roared. The feed horn positioning, motor sounded like a sewing machine on amphetamines. But when they powered it up and pointed it at aircraft flying over Boston Harbor, it worked. The prototype tracked 6 aircraft simultaneously, updated positions 3 times per second, calculated velocities within 2% accuracy, and maintained lock through clouds, rain, and atmospheric interference. Colonel Thomas Reeves, from the Army Signal Corps, came to see the demonstration. He was the officer responsible for anti-aircraft radar procurement, a man who had reviewed dozens of failed proposals and wasted prototypes. He watched the demonstration in silence. 6 distinct tracks on the scope, each one updating smoothly. Velocity vectors displayed numerically. Predicted positions marked with crosshairs. All automatic. No operator input required beyond initial target acquisition. After 10 minutes, Reeves asked, "How many targets can it actually track?" Getting answered honestly, "We do not know. The prototype is tracking 6. The mathematics says 30 should be possible. But we have not tested that because we cannot get 30 aircraft over Boston simultaneously." Reeves pulled out a notepad and did quick calculations. If you can track 30 targets, update 3 times per second, and maintain fire control accuracy through weather, then one radar can direct every anti-aircraft gun within a 2-mile radius. That changes everything. How soon can you build a field-ready unit? Getting said 6 months. Reeves said he needed it in 3. The Battle of Britain was over, but the Luftwaffe was still attacking English cities. American bombers were beginning daylight raids over Germany and taking horrific casualties from German anti-aircraft fire. The Pacific theater was a disaster. Japanese air superiority was absolute. The Navy was screaming for better anti-aircraft defense. Ships were being sunk by kamikaze attacks because gunners could not track targets fast enough. 3 months was not a request. It was an order, backed by the full industrial might of the United States at war. The radiation laboratory went into emergency production mode. Getting's team expanded from 5 engineers to 50, then 100, then 300. Machine shops ran 24 hours a day, fabricating components. Western Electric, RCA, and General Electric received contracts to mass-produce subassemblies. The design was finalized, tested, revised, tested again, and frozen into production specifications within 6 weeks. They called it the SCR 584, Signal Core Radio number 584. The name was deliberately boring. It revealed nothing about the revolutionary technology inside. To anyone reading procurement documents, it was just another radar set in a long list of military equipment. In reality, it was the most sophisticated fire control system built by any nation during World War II. The production units looked nothing like Getting's prototype. Everything was miniaturized, ruggedized, and integrated into a system that could be towed behind a truck, set up in 30 minutes, and operated by a crew of 4 with just 2 weeks of training. The antenna assembly fit in a trailer 8 feet wide and 12 feet long. The transmitter, receiver, and computer fit in a second trailer of identical size. Total weight, including generators, 4.5 tons. Power consumption, 10 kilowatts. Maximum detection range, 40 miles for large aircraft, 25 miles for fighters. Tracking capacity, 100 simultaneous targets. That number shocked everyone, including Getting. The prototype tracked 6. The production units tracked 100. The difference was vacuum tube speed. When the engineers built the final computer using the latest high-speed tubes from RCA, the processing rate jumped by a factor of 16. Suddenly, the bottleneck was not computation, it was display. The radar scope could not show 100 distinct targets without overlapping symbols making the display unreadable. They solved this by implementing priority filtering. The system automatically ranked targets by threat level based on speed, heading, and distance. The display showed the top 30 threats. The computer tracked all 100 but only displayed the ones that mattered. Gun directors received data on every target within range. Human operators only saw what they needed to see. The first production units came off the assembly line in January 1943. By March, 12 systems were deployed to England for field testing. By June, 100 systems were in operation across England, North Africa, and the Pacific. By December, 400 systems were operational worldwide. Production peaked at 80 units per month. The Germans noticed immediately. They did not understand how, but they knew something had changed. Luftwaffe bomber crews flying night missions over England reported anti-aircraft fire of impossible accuracy. Shells would detonate precisely at their altitude, even through solid cloud cover. Evasive maneuvers did not help. The guns tracked them through every turn, every altitude change, every speed variation. Bomber losses jumped from 12% to 31% in a single month. Colonel Josef Schmid, commanding Luftwaffe intelligence, reviewed the reports and concluded the British had developed some kind of infrared detection system that could track engine heat through clouds. German scientists dismissed this. Infrared could not penetrate thick clouds or operate in rain. The reports did not match infrared capabilities. Schmid's next theory was acoustic detection. Maybe the British had perfected sound ranging, using microphones to triangulate bomber positions. This theory also failed. Acoustic detection could not provide the precision tracking described in the reports. The truth, that the Allies had built radar systems capable of tracking dozens of aircraft simultaneously and calculating firing solutions automatically, never seriously occurred to German intelligence. Their own radar systems could barely track one target at a time. The idea that the Allies had leapfrogged to multi-target tracking seemed technologically absurd. By mid-1943, the SCR 584 was proving its worth across every theatre of war. In England, anti-aircraft batteries equipped with SCR 584 systems were destroying German bombers at rates 4 times higher than conventional visual aiming. In North Africa, American gunners used SCR 584 radar to shoot down Luftwaffe fighters attacking supply convoys. The accuracy was so good that pilots reported being hit by the first burst of fire before they even knew they were under attack. In the Pacific, the Navy adapted SCR 584 systems for shipboard use. The results were dramatic. Kamikaze attacks, which had been devastating American carriers, suddenly became far less effective. Ships could detect incoming aircraft at 25 miles, track them continuously, and direct concentrated fire from multiple gun mounts. Instead of gunners visually aiming at fast-moving targets and missing 90% of shots, radar-directed fire hit 60% of targets. That 6-fold improvement in accuracy was the difference between survival and sinking. But the most important test came in December 1944, when the Germans launched Operation Bodenplatte, a desperate attempt to destroy Allied air power in Western Europe by attacking airfields across Belgium, Holland, and France. The Luftwaffe assembled every operational aircraft they had, over 1,000 fighters and bombers, for coordinated surprise attacks on 15 Allied airfields. The operation was supposed to launch at dawn, when Allied fighters were still on the ground and anti-aircraft gunners would be blinded by low sun angles. The Germans achieved complete tactical surprise. Allied intelligence had no warning, but tactical surprise meant nothing against SCR 584 radar. At 05:32 on January 1, 1945, radar operators across Allied-controlled territories detected massive formations of aircraft approaching from Germany. Within 3 minutes, every anti-aircraft battery within 50 miles received targeting data. Mobile SCR 584 units were rushed to threatened airfields. The Germans arrived expecting to catch Allied aircraft on the ground and face minimal anti-aircraft opposition. Instead, they flew into the most intensive radar-directed anti-aircraft fire of the entire war. The Luftwaffe lost 370 aircraft in 6 hours, over 300 pilots killed or captured. It was the single largest one-day loss for German air forces during the entire war. Many of the aircraft were destroyed before they reached their targets. Those that got through faced such intensive fire that accuracy was impossible. Bombs fell in fields and forests. Few airfields suffered significant damage. The Germans called it Operation Bodenplatte, the baseplate operation. Historians call it the death of the Luftwaffe. Without those experienced pilots and irreplaceable aircraft, German air power collapsed. Allied bombers flew over Germany with near impunity for the final 4 months of the war. The SCR 584 was critical to that victory. Not because it was perfect, the radar had flaws. The feed horn positioning motor wore out quickly and required constant maintenance. The vacuum tube computer overheated in hot weather and needed frequent recalibration. The display scopes were dim and hard to read in bright sunlight. Operators needed extensive training to interpret priority filtering and avoid ignoring real threats. But despite these flaws, it worked. It gave Allied gunners eyes that could see through clouds, track through darkness, predict the future, and kill with mechanical precision. Technology that, 3 years earlier, every expert had declared impossible. If you find this story engaging, please take a moment to subscribe and enable notifications. It helps us continue producing in-depth content like this. Let me give you perspective on what SCR 584 really meant on the ground. January 1945. Bastogne, Belgium. The Battle of the Bulge was ending. German forces were retreating, but they were not defeated. The Luftwaffe still had enough aircraft for spoiling attacks, harassment raids designed to disrupt Allied supply lines and slow the advance into Germany. Sergeant Robert Hayes, a 23-year-old gunner from Texas, was operating an M51 quad-mount 50 caliber machine gun position, protecting a critical road junction. Hayes had been in combat since Normandy. He had shot at dozens of German aircraft, hit maybe 3, confirmed kills 0. Visual aiming against fast-moving aircraft was nearly impossible. You led the target, fired, hoped you guessed correctly. Usually, you did not. On January 8th, his unit received an SCR 584 radar system. Hayes and his crew got 4 hours of training. The training consisted of one sentence. When the radar tells you to fire, fire. When it tells you to stop, stop. Do not think, just do what the box says. At 1400 hours, the SCR 584 detected 8 German fighters inbound from the northeast, range 18 miles, altitude 6,000 feet, speed 320 miles per hour. The radar calculated intercept solutions and transmitted data directly to Hayes's gun director. A small receiver box mounted on his gun mount displayed 2 needles, elevation and traverse. Hayes was told to keep both needles centered. That is it. Center the needles, fire when the green light illuminates, stop when it goes red. The German fighters came in low and fast. Hayes could not see them. Cloud cover was solid from 4,000 feet to 10,000 feet. He just watched his needles and followed their instructions. The needles moved. He tracked them with his gun mount. The green light came on. He fired. For 11 seconds, all 4 50 caliber barrels poured rounds into empty grey sky. The green light went out. He stopped firing. Silence. Nothing visible. No explosions. No falling debris. Hayes assumed he had missed. Then a Focke-Wulf 190 fighter tumbled out of the clouds, one wing gone, trailing smoke and fire. It impacted 200 yards from Hayes's position. He had hit a target he never saw with a burst of fire guided entirely by radar. Hayes later said, "It was the strangest thing I ever experienced in combat. I was shooting at nothing, following instructions from a machine, and killing an enemy I could not see. It felt like science fiction. It felt like cheating. It was not cheating. It was physics." Ivan Getting's useless understanding of cosmic ray detection had created a fire control system that removed human reaction time from the equation. The gun did not care if the target was visible. The radar saw it. The computer calculated where it would be. The gun fired. The target died. Human eyes were irrelevant. By February 1945, Hayes's battery had confirmed kills on 23 German aircraft. He personally saw 4 of them. The other 19 were destroyed through clouds, in darkness, or at ranges where visual identification was impossible. Similar stories played out across every front where SCR 584 systems were deployed. In Italy, radar-guided anti-aircraft batteries protected the Anzio beachhead from German air attacks. In the Philippines, SCR 584 systems defended MacArthur's invasion fleet from kamikaze attacks. In France, mobile radar units advanced with Patton's Third Army, providing continuous anti-aircraft coverage during the race across Europe. The psychological impact on German and Japanese pilots was severe. They could not understand how Allied gunners were achieving accuracy that seemed superhuman. Evasive maneuvers did not work. Cloud cover did not provide protection. Night attacks were no safer than daylight raids. Luftwaffe pilot Hans Joachim Marseille, one of Germany's highest-scoring fighter aces, described the experience in his journal before his death in September 1942. "The Americans have some new weapon. Their anti-aircraft fire tracks us through clouds with impossible accuracy. Yesterday, I led a flight of 6 fighters to attack a bomber formation. We approached from above, through solid cloud cover, planning to dive through and engage from an advantageous position. Before we cleared the clouds, anti-aircraft fire found us. Not random spray. Precise bursts at our exact altitude and position. We lost 2 aircraft before we even saw the enemy. This is not skill, this is something else. Marseille never learned what that something else was. He died 2 weeks later when his aircraft's engine failed, but his journal captured what dozens of German pilots experienced, an enemy that could see them when they should have been invisible. By mid-1945, German pilots called Allied airspace Der Hexenkessel, the Witch's Cauldron, a place where invisible forces tracked you, predicted your movements, and killed you with mechanical precision. Japanese pilots had similar experiences. Commander Mitsuo Fuchida, who led the attack on Pearl Harbor and survived the war, wrote extensively about the evolution of American anti-aircraft capabilities. In 1942, Fuchida said, "Attacking American ships was dangerous but manageable. Gunners relied on visual tracking. If you came in fast and low, used cloud cover intelligently, and varied your approach patterns, you had reasonable odds of survival." By 1944, he said, attacking American ships was suicide. Their guns track through clouds and darkness. They fire before you are visible. Evasive maneuvers are detected instantly and countered. It is as if every gun is aimed by the same brilliant tactician who can see everything simultaneously and predict every movement. We call it Akuma no Mi, the devil's eye. Our pilots fear it more than they fear death. The devil's eye was a truck-mounted radar system that weighed 4.5 tons and cost $12,000. The same system that Colonel Thomas Rives had ordered into production in 3 months, despite every expert saying it could not be done. But the real story is not the radar itself. It is what happened to the technology after the war. Because the SCR 584's impact did not end in 1945. It fundamentally changed how humans thought about information processing, multi-target tracking, and automated decision systems. After Germany surrendered in May 1945, Allied technical intelligence teams swept through captured territories, cataloguing German weapons and technology. They found advanced rocket programs, jet engines, chemical weapons, and sophisticated radar systems, but nothing comparable to SCR 584. German radar technology was excellent for single-target tracking. Their Würzburg radar was actually superior to early Allied systems in some respects. But they never developed multi-target tracking. They never built automated fire control computers. They never integrated radar and guns into unified systems where the radar made aiming decisions without human input. Interrogations of German scientists and engineers revealed why. They had considered multi-target tracking theoretically possible but practically impossible. The computational requirements seemed insurmountable. German engineers calculated that tracking 10 targets simultaneously would require a computer weighing over 2 tons and consuming 50 kilowatts of power. Mobile deployment was impossible. Even stationary installations seemed impractical. They were correct about mechanical computers. Where they failed was in not considering vacuum tube computation. Germany's electronics industry lagged behind America's in vacuum tube technology. German tubes were larger, less reliable, and consumed more power than American equivalents. This seemingly minor technical difference cascaded into strategic consequences. Because German engineers did not have access to compact, high-speed vacuum tubes, they never seriously explored electronic computation for fire control. They assumed, reasonably given their available technology, that multi-target tracking was impractical until computing technology advanced significantly. They were right. But computing technology had advanced significantly. In America, not in Germany. Ivan Getting's team at MIT had access to RCA's latest vacuum tubes, Western Electric's manufacturing precision, and Bell Labs' circuit design expertise. They built a computer that German engineers thought was impossible because they were working with technology German engineers did not have. This is a critical lesson from World War II. Technological superiority does not come from having better scientists or smarter engineers. It comes from having better industrial infrastructure, better supply chains, and better integration between research and manufacturing. German scientists were brilliant, Their theoretical physics was world-class. But they could not build an SCR 584 because their industrial base could not produce the components required. After the war, the United States brought dozens of German scientists to America under Operation Paperclip. These scientists, many of whom had worked on advanced weapons programs, were stunned by American industrial capabilities. Werner von Braun, the German rocket scientist who later led America's space program, toured American factories and laboratories in 1946. He later wrote, "What impressed me most was not American scientific knowledge, which was comparable to German knowledge, but American production efficiency. In Germany, we would design a rocket engine and then spend months fabricating components by hand. In America, they would design a radar system and have thousands of units in production within weeks. The gap was not in what we knew, but in what we could build at scale." The SCR 584 exemplified this perfectly. The physics behind it was not secret. Multi-target tracking was theoretically possible, and German scientists knew it. But knowing something is possible, and actually building it, are completely different challenges. American industry could produce 80 SCR 584 units per month because American factories had precision machining equipment, standardized components, and trained workers capable of assembling complex electronics reliably. Germany had none of these advantages by 1943. Their factories were being bombed, their supply chains were disrupted, their skilled workers were drafted into the military. Even if German engineers had designed something equivalent to SCR 584, they could not have built it at scale. The war would have ended before the first units reached the field. Getting himself returned to academic research and joined Raytheon Corporation. His most important contribution came in 1951 while working on intercontinental ballistic missile guidance. The problem was navigation accuracy over 5,000 miles. Getting proposed putting precise clocks in orbit and using timing signals to calculate position. If you received signals from multiple satellites simultaneously, you could triangulate exact position. The physics was identical to radar ranging and multi-target tracking. The military funded development in 1964. The first satellite launched in 1978. The system became operational in 1993. We call it GPS. The technology in your smartphone, guiding your car, tracking aircraft worldwide, came directly from Getting's SCR 584 work. The principle is identical. Multiple signals processed simultaneously, precise timing, calculating position, automated computation, producing results without human interpretation. Getting died in October 1993, just as GPS became operational. Today, over 4 billion people use GPS daily. The economic value exceeds $60 billion annually, and it traces back to a physicist studying cosmic rays. But GPS was not the only legacy. Modern air defense, air traffic control, tracking thousands of aircraft simultaneously, weather radar following storm cells, all use multi-target tracking algorithms developed at MIT in 1942. When Ivan Getting proposed electronic beam steering and multi-target tracking, every established radar expert told him it was impossible. They were applying professional knowledge to reach the logical conclusion that the proposed solution violated known constraints. They were right about the constraints, but they were wrong about the conclusion. Getting was thinking about what might be possible if you changed the constraints. Instead of accepting slow antenna rotation, use fast feed horn positioning. Instead of accepting limited analog computation, use high-speed vacuum tubes. Each solution seemed impractical in isolation, but combined, they worked. This is why outsiders matter. Getting came from cosmic ray physics, not radar engineering. He did not carry the institutional knowledge that said certain things were impossible. He just saw a physics problem and applied physics solutions. Colonel Thomas Reeves could have dismissed Getting's proposal as unrealistic, but he was desperate enough to gamble on an outsider with a crazy idea. That willingness to fund unconventional approaches was one of America's great advantages during World War II. One decision by one colonel changed the course of anti-aircraft warfare and eventually led to GPS. Imagine if Reeves had said no. The SCR 584 would not exist. Allied anti-aircraft defences would have remained mediocre, and in the long term, GPS would not exist. Air traffic control would be less safe. Weather forecasting would be less accurate, all because one decision-maker said yes instead of no. By April 1945, as the war in Europe ended, over 800 SCR 584 systems were deployed across every theatre. They had collectively tracked over 50,000 enemy aircraft and directed fire that destroyed approximately 6,000 planes. That is a 12% kill rate, which might not sound impressive until you realize that pre-SCR 584, the kill rate for anti-aircraft fire was roughly 1%. A 12-fold improvement in lethality from a single technology. German and Japanese forces never developed an effective counter. They tried several approaches. Low-altitude attacks to stay under radar coverage did not work because SCR 584 could track targets down to 500 feet. High-altitude attacks were even worse because the radar's range increased with altitude. Electronic jamming was attempted, but SCR 584's frequency-agile transmitter could hop to clear channels faster than jammers could follow. The only effective counter was to not fly at all. By May 1945, the Luftwaffe had essentially ceased to exist as a functional air force. Japan's air forces were shattered, reduced to kamikaze attacks because trained pilots were too valuable to waste on missions with high attrition rates. The SCR 584 did not win the war alone, but it contributed significantly to air superiority, which enabled everything else: bombers that could strike without fighter escort, invasion fleets that could land without air cover, supply lines that operated without constant air attack, every advantage built on the foundation of controlled airspace, and controlled airspace required the ability to destroy enemy aircraft reliably. That is what SCR 584 delivered: reliable, consistent, automated destruction of aerial threats. In 1942, shooting down an enemy aircraft required skill, luck, and favorable conditions. By 1945, it was a mechanical process. The radar saw it. The computer calculated the solution. The gun fired. The aircraft died. Human factors were minimized. The system worked, regardless of visibility, weather, time of day, or operator skill. You could take a crew with 2 weeks of training and make them as effective as veterans with years of combat experience. That democratization of effectiveness, making lethal capability available to anyone who could follow simple instructions, changed warfare permanently. Modern military doctrine is built on this principle. Advanced weapons systems are designed to be operable by soldiers with minimal training, point-and-click interfaces, automated targeting, simplified controls. The goal is to put maximum capability in the hands of maximum personnel. That concept traces directly back to SCR 584. Before that system, anti-aircraft defense required highly trained specialists. After it, anyone who could center 2 needles and press a trigger could shoot down aircraft. Ivan Getting did not live to see all the implications of his work. He died at age 91, just as GPS was proving its revolutionary potential. But in his later years, he reflected on what the SCR 584 meant to him personally. In an interview conducted in 1992, 1 year before his death, Getting said, "I am proud of the technical achievement. Multi-target tracking was a hard problem, and we solved it. But what I am most proud of is that we saved lives. Every aircraft we shot down was one that could not bomb a city or sink a ship. Every convoy that reached port safely, every city that was not burned, every soldier who came home because our defenses worked, that is what matters. The technology is interesting to engineers and historians. The lives saved are what matters to human beings." That perspective, keeping focus on human impact rather than technical cleverness, characterized Getting throughout his career. He was a physicist who understood that science existed to serve humanity, not the other way around. His work on GPS was motivated by the same concern. Better, Navigation meant fewer aircraft accidents, fewer ships lost at sea, fewer military casualties from friendly fire. The technology was fascinating, but the lives saved were the point. This is worth remembering in an age where we often celebrate technology for its own sake. The question should never be, is this technically impressive? The question should always be, does this make human lives better? Getting's career answered that question consistently. Yes, his work made lives better. Thousands of lives saved during World War II, millions of lives improved by GPS, billions of people benefiting from technologies derived from his innovations. There is a memorial at the Aerospace Corporation headquarters in El Segundo, California, where Getting worked for over 2 decades. It is a simple plaque with his name, dates, and a brief description of his contributions to satellite navigation. Most people walk past it without a second glance. They do not know who Ivan Getting was. They have never heard of SCR 584. They might use GPS every day without knowing where it came from, and that is fine. Getting did not do the work for recognition. He did it because the problems were interesting and the solutions might help people. The anonymity of his contribution is, in a way, a measure of his success. When technology works so well that people forget it is technology, when capabilities seem natural rather than revolutionary, that is when engineering has truly succeeded. Nobody thinks about radar systems when they check their weather app. Nobody considers multi-target tracking algorithms when GPS guides them to a destination. The technology fades into the background, and people just experience the benefits. That was Getting's gift to the world. Technology that works so reliably, so seamlessly, that it becomes invisible. Let me close with one final story. December 1944, Antwerp. Corporal James Mitchell, the radar operator who tracked 63 V-1 flying bombs, simultaneously and saved 2,000 lives. He survived the war, returned to Ohio, and worked as an electrical engineer for General Electric until he retired in 1982. Mitchell never talked much about his wartime service. His family knew he had operated radar equipment. They did not know about the V-1 attack or the lives he had saved. In 2004, a historian researching the V-1 campaign discovered Mitchell's name in operational reports. The historian contacted him, then 81 years old, and asked if he remembered December 16th, 1944. Mitchell said he remembered it clearly. It was the only time during the war when he felt like he had personally made a difference. The historian asked if Mitchell understood the significance of what he had done. Mitchell said, "No, not really. He just did what he was trained to do." The historian explained that Mitchell's action, tracking and directing fire against 63 Von Second, had prevented the place's destruction of Antwerp port. Without that port, the Allied advance into Germany would have stalled. The war might have lasted months longer. Thousands more lives would have been lost. Mitchell's response, captured in the historian's interview notes, was simple and moving. "I was just turning dials and reading a screen. The radar did the work. I just watched it and followed procedures. If I made a difference, it was because someone built a machine that could see what I could not see and calculate what I could not calculate. I was just the operator. The machine was the hero." That statement captures something profound about World War II and about technology itself. Individual heroism still mattered. Courage, sacrifice, determination. Those human qualities won the war, but they won because technology amplified them. Mitchell was brave. But bravery alone could not track 63 targets simultaneously. The SCR 584 could. Getting was brilliant. But brilliance alone could not make radar. Beams switch faster than mechanical rotation allowed. Vacuum tube circuits could. The war was won by humans and machines working together, each contributing what the other could not provide. The lesson is that we need both. We need brilliant individuals who question assumptions and imagine what might be possible. And we need institutions that support them, fund them, trust them, and give them the resources to turn imagination into reality. Ivan Getting studied cosmic rays because he was curious about the universe. That curiosity led to insights about multi-target tracking. Those insights led to SCR 584. That system saved thousands of lives, contributed to victory in World War II, and eventually led to GPS. Today, 4 billion people use technology derived from one man's curiosity about cosmic radiation. That is the power of basic research. That is why we fund science. That is why we support people asking questions that seem useless. Because sometimes, the most useless questions lead to the most useful answers. Thank you for watching. For more detailed historical breakdowns, check out the other videos on your screen now, and don't forget to subscribe.